Hello everybody, it's Mr. Gus and I am back in the physics classroom. Today we're talking about circles. What causes objects to move in circles? How is it different than moving on a line like we've been discussing? So far we've discussed objects that move left to right, they move up and down, they move down a ramp, they move up a ramp, they may move in projectile motion. All of these things have generally taken movement in one of two directions. They've either moved in the X or horizontal directions or parallel directions, or they moved in the Y direction, vertical direction, or perpendicular direction. All these things are up and down relative to some axis, but none of these things have actually looked at things moving in circles. So let's talk about that. We have so far studied a couple of things. Let's go back in the past a little bit. We've talked about forces and how they impact velocity. So I have an object that is moving in this direction in three different cases, right? This is the speed of the object moving this way. If there is a net force acting on that object in the same direction that it's moving in, we called this speeding up. We had a name for that. We said if there is an acceleration in the direction of motion or a net force in that direction, we call that speeding up. If that net force was in the opposite direction of the direction of motion, or at least some component was opposite of it, we called that slowing down. We have not really at length discussed what happens if there is a force that is perpendicular to the direction of motion. We have not done this, but if I think about this, I mean, we did it in our projectile motion, right? If I had an object that was leaving an incline, it was moving this way, and the force of gravity was on it, we saw that it would turn. It would actually kind of go from horizontal to the Y direction. So we can kind of ascertain from that is that perpendicular forces to motion cause changes in direction. And so it seems like we have three ways that we can accelerate. We know that net forces cause accelerations. This is our theme of the course. Outside forces cause changes in motion. And so if the forces are in the same direction or some portion in the same direction as the velocity, we see a speeding up. If the force is in an opposite direction of motion, it is slowing down in some way. And then, I guess, thirdly, if there is some amount of perpendicular force to an object's motion, it will change the direction of that object. We saw it in kinematics. But here for a circle, it's almost as if it's got to constantly change directions. If I think about a circle is an object that moves in a circle, wants to move linearly, but is repeatedly being pulled back into this type of path, into this circular path. So let's examine that a little further. I've got a hover puck that will reduce friction when I turn it on, and it's attached to this string. Let's go play around with it on the floor. So if I get my camera over here, I'm hoping that maybe you can see this if I lower it down to the ground, and what do you know, you can. So I'm gonna go ahead and turn this puck on, and as you know, if I just give it a simple tap across the floor, it moves in constant straight line motion. Now we know that the friction is being reduced by the fan. I only applied a small tap, and so without any other outside forces acting on it, it will continue to move at that constant velocity across the floor. That's our typical type of motion. But what's crazy is that if I have this object on a leash like I do, and I go ahead and I hold that leash down to the ground, creating a radius, and I give it that same gentle tap, what's going to end up happening is that that force, oh, it hit my foot. I need longer arms, I'm too short for this. Let's try it again. If I give this thing a gentle tap, it doesn't go in a straight line anymore. It wants to go in a straight line. We know this because that's what it did, but instead it takes this circular path around my finger. And it's getting shorter because I have it wrapping around my finger, but you see that it wants to go straight, and if I let it go at the right time, it will go straight. It just carries on moving straight. But apparently, having that string attached causes a weird change in motion. It causes a circular motion. So if I think about what causes that, the only difference between what was going on before and afterward is that there was a force. My hover puck that typically moved in this straight line fashion, when I attached a string to it, and that string provided inward tension, and that tension was being pointed inward over and over and over again, this constant inward tension force caused that object to move in a circle. It's different than gravity in our free fall stuff. It's a constantly changing force. It's constantly pointed towards the center of my circle. And so we have a different direction. It's not like a vertical direction force always. It's not a horizontal direction force always. It's a different type of direction. So let's name that. Because it's different, we have to give it a new name. And so we're going to call any force that points inward, constantly inward, we're going to call that a centripetal force. Let's make sure we define it now. A centripetal force is a net force. And in our case with the hover puck here, it was a tension force, but it's any force, a net force that is pointed in the direction of the middle of a circular path. And so, for example, we could have our hover puck here. I'm not very good at drawing what that soccer ball looked like, but it looks something like this. And there was a center of my circle, and there was a string acting on it. This soccer ball was moving forward, but there was an inward tension force that caused this thing to move in a terribly drawn circle. So in our case, I would have said the centripetal force is equal to the tension force in this case. Those would be synonyms because the tension force is a net force that is pointed in the direction of the middle of a circular path. This is what we would call a centripetal force. Now, if I went ahead and thought about the moon in orbit around our Earth, a tension force doesn't hold our moon in its roughly circular orbit. Rather, gravity does. The weight of our planet attracts the weight of the moon. So gravity, in that case, would be the centripetal force through that roughly circular orbit. So centripetal forces change. They're simply defined as a force that is pointed in the direction of the middle of a circular path. Kind of like X direction forces are horizontal forces, and Y direction forces are vertical forces. Centripetal forces are just forces that are pointed towards the middle of a circle. It's a new kind of direction that we're talking about here, okay? And because we're talking about centripetal forces in circular paths, we're going to have to break down some other definitions. And there are some words that pop up early in this unit that we have to refresh our memories on. There's a couple words like period. Period is a word that shows up pretty regularly. It's got a variable of capital T, and it's defined as the time an object, not it, an object takes to make one circular path. Okay? This is our period. We can go ahead and measure the period over there if we wanted to. You can go back and measure the period on the hover puck. Second definition that we learned in chemistry but pops up again here is frequency. Frequency is lowercase f, and this is defined as the number of revolutions or number of circular paths in 1 second. These things sound familiar or related because they are. Period is the inverse of frequency, and so therefore, frequency is the inverse of period. Let's go ahead and do a rough calculation, okay? Let's do a rough calculation over here. Let's figure out what the period of this hover puck is. So I'm going to go ahead and turn it back on, put it down. I want to figure out the rough time for this thing to make one loop. All right, are you ready? I'm gonna go this way this time. At home, you go ahead and time this yourself. I'm just gonna do a rough time verbally. Okay, you ready? 3, 2, 1, go. 1, 2, 3, 4. All right, I'm gonna say like 4.2 seconds. Maybe I'm totally wrong, I don't know. I'm gonna say it took 4.2 seconds to go around that path. I could be totally wrong. It's a Monday morning, maybe my mental timing skills are off, I don't know. But let's say that the hover puck, for example, had a period equal to 4.2 seconds. That would be how long it took to go around that circular path. Well, its frequency, if I was asked what is the frequency of that, it would be equal to the inverse, or 1 over 4.2 seconds. So roughly, I don't know, closer to 0.2, 0.23, somewhere around there. It'd be whatever the inverse of that is my frequency. They are inverses of each other, okay? And a very common unit of frequency is hertz. H-E-R-T-Z. H-Z is its abbreviation, and all a hertz is hertz. The unit is the same as 1 over seconds. It's a common unit used for frequency, and it simply means the inverse of seconds, which is, it makes sense given the fact that we have, it is the inverse of period, okay? So there's an example of frequency and period and what those might be. Now, thinking even further, if I want to think about the speed at which that object was moving, it was moving in a circle. So it's weird to talk about velocity, because if I'm talking about the velocity of this object, its displacement every revolution is 0. So it's really strange to ask, like, what was the circular velocity? Because technically, every time it gets back to the same spot it started at, it's resetting its displacement. So displacement is weird here. It's not weird, it's just not useful. It doesn't help us explain the motion. And so velocity doesn't help us explain the motion. So we're going to focus more on speed here. So let's revisit our old definition of speed. If I think back to what speed was, back way in Unit 1, we defined speed mathematically. This was just our distance, our total distance traveled in a certain time frame. All right, so that's all we're going to be doing here. In order to find how fast this hover puck was moving, we got to figure out how far it traveled and how long it took to travel that path. So if we think about the example again, the example of our hover puck, here was the puck. Again, I'm not great at drawing soccer balls, but that's close enough. There's my hover puck. It was attached to a string and made a circular path. Again, terrible circle, but there's the circular path. How far did it travel? Well, it traveled this far. It traveled all the way around the circle. Mathematically, I know what that is. That's a circumference, right? Around the circle, that measurement is a circumference. That's how far it traveled. Circumference is 2 pi r. If I forgot that, it's on my equation sheet under the geometry stuff. So in order to figure out how far this thing traveled, the distance, I got to know the circumference. And then I got to ask myself, how long did it take to travel the circumference? Well, that's the period. Right? We have kind of another sidebar definition of period. Period is the time to travel one circumference. Okay? So from this understanding, I can build myself a little equation. If speed is distance over time, and circumference is the distance, and period is the time over that distance, my equation becomes velocity of a circle, or speed tangential as we call it, is going to be 2 pi r over the period. And we call it tangential speed because we know the object wants to move or is attempting to move on that tangential path, the path that is on a straight line away from the circle, but that force, this inward tension, inward centripetal force, is holding it in the circle. So if I think about at any point on my circle, that hover puck wants to be moving in these directions. All the way, it wants to go that way, but as we talk about changing directions and centripetal forces change directions, that's what this tension force is doing, is it keeps pulling that hover puck back around in its circle. So we talk about the speed tangentially, or the V tan, is equal to 2 pi r over t. Let's find out how long that string was, and then I'll let you guys go ahead and calculate at home what the speed of this object was. So I've got my string, I've got my meter stick. It looks like this string has a radius of 53.5. Okay, so if I think about radius, 0.53 meters. This is my radius. So go ahead at home and calculate what is your tangential speed. It should be straightforward. 2 pi times r over the period that we calculated or measured over here. And again, our period was 4.2 seconds. This would be a way to calculate my tangential speed. Other definitions that may pop up and things you may see are revolutions per minute, RPMs. All of these ideas still fit in the framework of what we discussed here with frequency, with period, with speed, and with centripetal force. Okay? These are some of the basics you'll need to know, some definitions that might help you sort through some things as you think about beginning your study of circular motion. All right? I hope this helps. Till next time, see ya!